For this lab, we're going to study centripetal acceleration. And in order to do this, we're going to compare forces from two methods. One method where we balance the force of a spring against force of gravity, one where we spin it and calculate that the centripetal acceleration is caused by the spring. Then we're going to calculate the spring constant, which is just how stiff the spring is. So let's talk a little bit about the force that the spring's exerting. And this force is given by Hooke's law, which is force of the spring equals negative kx, where this is stretch of spring from its equilibrium point, so from where it started. Then we have k, which is the spring constant. This is just how stiff the spring is. And then you'll notice this negative sign right here. And all that the negative means is that if you pull to the right, the spring pulls to the left. The second thing that we need to know is we are going to spin a mass. Blue didn't show up real. So we're going to spin a mass. It's going to go around here. It has some velocity tangential just around the outside. And if you'll notice, as it goes around, if there wasn't anything pulling it back to the center, it would just go off in a straight line. So there is a force pulling it to the center, and in this case, that force is from the spring. So in this lab, the sum of forces, and in this case, we're looking at the forces towards the center of the circle, equals m mass times the acceleration towards the center. So this force over here is caused by the spring, and this is m, and if you remember from class, this is v squared over r. So now we have to examine this v, and you know that v equals change in displacement over change in time. So let's examine how fast this goes. So if we look at this, delta x is distance around the circle. So that's going to be 2 pi r, and then times number of revolutions, over delta t, which is your time frame. Right? So plugging this into the equation above, we get the force from the spring equals m 2 pi r number of revolutions squared over delta t squared times your radius. Radius being just this radius of the circle. So the first way we're going to calculate force is by hanging masses until this little pointer right here matches the little rim of that UFO looking thing. I've got a better picture coming up here in a moment. So if we notice, there are two forces from our force diagram. We've got weight pulling down, the spring pulling up. It's not accelerating. So what you wind up with, force of the spring minus or plus, we'll say negative, weight equals 0 for a grand prize of the force of the spring equals mg. So that's one way to find the force. A couple notes on the apparatus. This scale is in 40ths of an inch, and that is a horrible unit, so we have to convert this. The second thing to note is that the delta x that you're going to be making your graph on is this distance, which is your radius, that goes to center line here to this line. This is your radius, plus however much this spring is stretched right here. So in your equation, your delta x when you graph is going to be equal to r plus, I'll just use this little delta x, but that is indicated by how far this is stretched over here. The second way we're going to find force is we're going to spin it in a circle. So attach it right here to this apparatus. Note, there is a belt right here. If you like it, don't put it next to the spinning belt. This is great for things like hair and your sleeves. This is going to spin around very, very quickly, and we'll show you that in a minute. So don't put your face or anything you like next to this. The key thing to look at is if we take a look, let's zoom in here. Again, when this is balanced, this pointer points right at the center of that rim. So let's watch this in action. And it's going to spin. And if you look right here, you can see this pointer. This is too slow, That's too fast. There's a little knob at the bottom of the machine. One partner is going to keep on spinning. So right now it's too fast. If it drops, it's too slow. You want it pointed right at the center of the little flying saucer looking thing. You have to constantly adjust in order to get this right. And you're going to do this multiple times. So a couple notes. The only mass that is spinning is this mass right here. And you'll notice it's conveniently written on the bottom. The second thing is timing. It moves really fast. It is hard to count. So record your start time and end time. Remember to include all of your raw data in your lab report. And you will spin it multiple times. The final thing to remember is that you're going to repeat this experiment for all of the different delta x values. Delta x is the stretch of the spring, or total delta x. So it's this little change right here, and every full turn you do is a 40th of an inch, so remember you're going to have to convert this to meters, and the delta x you're going to graph, the full stretch of the spring, is this radius plus this delta x. So data collection. Overall, you need the radius. This is from the center line to the middle of the mass. When you hang the mass, you just need mass of the hanger's mass, and the bob's mass, all three. When you are spinning it, you get the number of rotations over that set time, and the only thing spinning in that case is just the bob. So that's the only mass that enters that equation. Okay. Error analysis. You will compare your two forces. Compare forces. Okay. So the way you look at this, you will get the force from gravity, or we'll just call this the hanging method, equals your force from spinning. Which means you are going to get plus or minus, plus or minus. On this side, this is just plus minus your hanging masses. And let's take a look a little more in depth about the spinning masses, because they have a little bit more error in them. So when analyzing this, remember that you will always report a force plus or minus, and you're going to compare the force hanging to the force you get from spinning it. So you always want your average value, so you calculate it just with the averages, plus or minus the max possible minus your average. So to get the max value, if it's on the top, you want to use the biggest value of R, and the biggest values of number of revolutions. And if it is on the bottom, well, you want a big number, so you want the smallest R you measured on the bottom. So in short, big R is on top to get the biggest number, small r is on bottom. Remember you measured radius multiple times. And then that's how you'll get it. You'll get the max possible value minus the average, and you'll get a force minus this. And hopefully this error bound right here contains the springing constant, or the spring force that you got from the hanging mass. Let's look at the equation. So this is Hooke's law, and if we compare this to the equation for a line, y equals mx plus b, you will see that x is just delta x, which is your radius plus however far you stretch the spring, and your force of your spring is your y, and which means your slope is going to be k. So it's going to look like this, and you'll get your sum k, and you can report the value of the spring constant. And that's the last part of the lab.